Okay, let's jump right in. So, with any kind of 3D printing, you have post processing steps that can help boost the part's aesthetics and even the mechanical properties. SLA or resin printing is really no different, and I think some of the techniques we'll describe in this webinar are pretty unique and may unlock some interesting applications for y'all. Before we talk about the different post processing options, I want to take a moment to discuss the printing workflow for SLA printers in case anyone's a little unfamiliar. The process is threefold. It begins with a 3D model produced in a CAD program like SolidWorks. Then we export our part out into a common 3D file format like an STL, OBJ, or 3MF. We do this because our next step, the slicing software, accepts these file types. And in the slicer, we go in and we adjust print settings, things like material type, part orientation, and layer height. And the slicer automatically cuts the part into layers, generating the code necessary for the printer to then print the part. Here's a graphic showing kind of each step of the process. And I think it's pretty easy to see why that middle step is called the slicer. Now, if we're dealing with FDM printing, that would essentially be the end of the workflow. But SLA is a little bit different. That's because we're dealing with a liquid-based printing system. Once a resin part finishes printing, it has all this liquid resin coating it that we need to deal with before handling with our bare hands. This is where the wash comes in. After printing, we submerge the part in the wash, which agitates a solvent bath, the solvent typically being isopropyl alcohol. Washing takes no more than 20 minutes and is followed by at least 30 minutes of air drying. At this point, our part is free of any uncured resin and is now safe to handle. In most cases, our final step is the cure. Whoa, not that kind of cure. And I didn't mean final step as in final step of the week. Come on. Anyways, curing is responsible for exposing our part to a bit of heat and a lot of UV light to bring our parts up to their optimal mechanical properties. And the results, they pretty much speak for themselves. Resin printing is known for its ability to achieve very detailed, highly accurate parts with injection mold level surface finish. Unlike FDM, you can say goodbye to those layer lines. However, like FDM, SLA prints still have supports to deal with. But you can see pretty easily here that the support removal process for SLA is not only going to be easier, but the localized light touch support trestle leaves a cleaner interface once removed. Let's take a look at a comparison. Ooh, and on top of that, FDM parts requiring supports definitely have some unfriendly camera angles. All that said, support marks are still left behind on SLA prints after support removal, and these can stand out when juxtaposed to the very smooth, unsupported surfaces. So what is the best way to deal with these? Well, for starters, flush cutters, hobby knives, and tweezers all work really well to remove as much of the support as possible. Then it's just a matter of sanding, and as is typical with sanding, we want to start from coarser sandpapers like 150 and gradually work our way up to finer grit sandpapers like 1,000 and up. And you can see here the part is already looking a lot better. And you can also wet sand SLA parts, which helps keep the dust levels down. You just need to use things like mineral oil or water as the wet medium. Now, sanding doesn't have to be entirely manual. Formlabs actually provides finishing tools that make the process go a bit faster. And speaking of bits, this kit comes with a rotary tool, pen sander, and their corresponding accessories, and a few other tools like a hobby knife and microfiber cloth. Once the sanding is complete, you can apply mineral oil to the part to buff up the part, or paint on the same resin used to print the part and cure it to make the surface extra smooth. And a quick safety note, this process involves flying objects and dust. Yeah, I guess that does make it sound like we're tornado chasers or in The Wizard of Oz or something. But what I mean is to be sure to wear safety glasses, respirator, and gloves when doing this kind of work. And the juice is worth the squeeze. That's a pretty great looking part. Now, at this point, I think the big question is,
now what?
well, what now, huh? There are some pretty clever post-processing options available for SLA prints, the ones listed here being some of the most common. And of these, adding color really is the most common. Painting, dyeing, and printing with colored resin are all ways to achieve colored parts. When preparing to paint any plastic part, you want to first go through the preparatory steps that we just discussed. Then, it's a good idea to mount the part in preparation for priming. This can be done with either drilling a hole into the part or using hot glue to mount the dowel. Priming is a good practice because it helps to expose surface flaws and increase top coat adhesion and durability. Tamiya surface primer is really great, but primers from Rust-Oleum, Krylon, and Duplicolor also work. And these are just regular primers. Since SLA prints have no discernible layer lines, you don't need filler primer like you do with FDM prints. Spray the primer on in even strokes, keeping distance away from the part to avoid paint runs. Once the primer has cured, review the surface and make any corrections necessary. You can always add another layer of primer afterwards. Just note that fine details can vanish with added paint layers. At this point, you are ready for painting. Spray cans, airbrushing, and hand painting in acrylics, enamels, and lacquers are all great ways to color your printed part. Once finished, let the paint dry and consider adding a clear coat to seal the paint and increase its longevity. UV clear coats are great for protecting SLA prints in outdoor applications. Now, painting is really straightforward. I think a lot of you guys have experience with this already. But something that is a little unique is dyeing. There are actually two ways to go about this. The first way is to print with dyed resin. The second way is to dye the part after printing. If you want to print with dyed resin, that's our first option. The process involves adding 10 milliliters of alcohol ink directly to 1 liter of clear resin. You just add it directly into the cartridge. We use clear specifically because dyeing it does not impact print quality on the same level as other resins. Bear in mind, though, that adding any form of substance to resin may increase the chance of print failures and will void the warranty of the printer should an issue arise. Once you've added the dye to the resin, shake the cartridge thoroughly and then resume the normal printing, washing, and curing process for clear. Note that the wash solvent will become dyed, so you may consider using a separate wash, either a wash station or a wash bucket, to avoid unintentionally dyeing other prints. And here's the finished product. I think that blue dyed print looks pretty sweet. The other dyeing method is dyeing after printing. We are not limited to the resin type as before, although this process works best with clear, elastic 50A, and flexible 80A because of their translucency. In this process, we add 10 to 20 milliliters of that same alcohol ink to IPA, depending on your desired color saturation. This can be done in the form wash or in a separate bin. After your part finishes its normal wash cycle, transfer the part into the dyed IPA solution for 10 minutes. The rest of the process resumes normally with curing and so on. And here is the finished result for this method. You can see there is not much difference in the color saturation between parts dyed before or after printing. So it's probably best to dye after printing if you can, to avoid print failures and warranty issues. The last common way to add color is to simply print with Formlabs Color Kit. The color kit consists of an 800 milliliter color-based resin cartridge and 5 pigments: cyan, magenta, yellow, black, and white, with their corresponding 10 ml syringes. Choose your desired color and follow the pigment ratio listed in the accompanying recipe book. You can also refer to the custom color picker in the Formlabs store profile for color resin to choose a highly specific color. Note that each recipe requires 100 milliliters of pigment. Extract these, inject these into the color base, close the cap, and shake for about 4 minutes. From here, the printing process and all the rest proceeds normally. And check out the range of color options available. These prints look pretty great. You get the color variety of FDM with the awesome surface finish and accuracy of SLA. Now, I know I said the color kit was our final option for coloring our resin prints, but there's actually a pretty unique quaternary method that combines the color kit and dyeing. Instead of the color base, we're using flexible ADA, and instead of alcohol ink, we're using the pigments from the color kit. It's called the soft tissue starter pack because it's frequently sold to dental customers who use it to create things like gingiva masks. This is why the pigments are fewer, since we're trying to 3D print tissue models at varying degrees of vascularity. Rather than 100 ml pigment recipes, we're focused on only 40 mils. So we first extract 40 mils of flexible ADA from the cartridge, and then we add 40 mils of combined pigments to produce light, medium, and dark pink tissue tones. I wanted to bring this up because I thought it was kind of an interesting hybrid of techniques used here. So that covers it for coloring our resin prints. The next topic I want to cover is increasing the transparency of our clear resin prints. Before the advent of the Form 4, increasing optical clarity of clear resin was highly requested. This changed when the Form 4 entered the industrial SLA space. The Form 4 launch featured the debut of improved general-purpose resins at a lower price point. As a general-purpose resin, clear, transitioning from V4 to V5, now boasts superior mechanical properties and increased transparency. Check out the difference. V5 doesn't experience yellowing in the cure like V4 does. Even with the improvements, there are still ways to boost clarity. I came across this awesome video by Derailed 3D where he printed a bottle in clear V5 on the Form 4 and stuck a Benchy inside it. Straight out of the printer, the bottle looks incredible. Oh, and to get the Benchy inside the bottle, he paused the print job and worked his magic. Absolutely ingenious. The print was resumed and was washed and cured afterwards. Then the post-processing begins. He scores it with pumice substitute and then polishes it with tan high shine compound. Next, he applies mineral oil inside and out. After wiping the excess away, you can see how incredibly realistic it looks. Great work, Derailed 3D. A similar video from Formlabs LinkedIn showcases the same concept to produce an almost exact replica to a glass from their office. They use the same method as Derailed 3D, and I think this method works the best. But there are other options as well. You can use a general purpose 2K clear coat or an automotive clear coat if you want to go more professional. If you have a flat or nearly flat part, you can apply clear resin to the part by syringe, brush, or dipping. You can also technically apply clear resin to any of your parts. They don't have to be flat, but the flat ones usually showcase the clear result the best. Let the excess drip away and then cure it. Successive cycles will gradually increase clarity, as you can see here with these lenses. I've seen similar practices done, but with using clear floor polish instead. I mean, look at that, it looks like glass. So give these methods a try. I think y'all will be pleased with the results. All right, we're almost done here. These last two post-processing techniques are actually pretty similar in that they are both coatings. We'll start with Cerakote. Many of you are familiar with this product as it's common in many industries, such as firearms. It is a high-performance, thin-film ceramic coating developed by NIC Industries that is known for its excellent temperature, chemical, and UV resistance. Though typically known for its application to metal surfaces, NIC and its approved distributors and applicators have seen increasing requests for Cerakoted plastic parts, especially 3D printed plastic parts. The process involves media blasting the part with 100 grit aluminum oxide or garnet sand at 40 psi to etch the surface for adhesion promotion. The part is then wiped down with a cleaner, and then the part is Cerakoted via a spray applicator. This helps achieve the thin film description. Once uniform coverage is achieved, the part is post-cured at an elevated temperature or air-dried in ambient conditions. For most of you, this information is totally irrelevant as NIC has a list of approved applicators. These guys have all the equipment and experience and are happy to help you get Cerakoted parts. As we'll discuss in the next section, many believe that metal is the material they need for their application, but the geometry just doesn't lend itself to low-cost manufacturing or is impossible to manufacture. But with 3D printing and Cerakoting, you can get many of the mechanical properties of metal without huge expenditures. That is the power of composite materials. There are 4 primary series for 3D printed parts, and each have their strengths, so application details are key. H series is the most common for SLS and SLA parts, and is NIC's flagship coating. It is easy to apply and has over 150 colors and finishes. Elite series is very chemically resistant. C series is the most temperature and UV resistant. And the last series, MC, is also UV resistant, but adds self-lubricating properties as well. So it makes a great mold release coating for those rigid 10K and high temp resin injection molds. Check out some of these Cerakoted SLA and SLS parts. The great thing about Cerakoting SLA parts is that there is no porosity, so you're not having to first vapor smooth or apply excess Cerakote applications. And with the popularity of Cerakoting, NIC has seen needs in pretty much every industry, from aerospace, consumer goods, oil and gas, medical devices, and general manufacturing. Okay, last topic here, electroplating. As I mentioned in our last section, this is another coating, and like Cerakote, it produces some awesome high-performance parts. Electroplating is often called the closest thing to metal 3D printing because the result is not a true metal part, but it captures most of metal's mechanical properties without the cost, training, and infrastructure burdens. You can think of electroplating as bridging the gap between metal parts and SLA printed parts. Look at this lattice, for instance. This is a very geometrically complex part. To manufacture this traditionally would be nigh impossible. To 3D print this in resin, though, is very simple. To 3D print this in metal is possible, but requires a lot of upfront costs and technical know-how. Problem is, this lattice has to bear the full weight of a human. In TUF 2000, one of Formlabs' most popular engineering-grade resins and an ABS mimic, it didn't survive, failing at about 60 pounds. So, how can we increase the strength without changing tech or the base material? Well, we can electroplate it. After plating with majority nickel and some copper, the lattice was bearing 300 pounds without failure. As I said with Cerakote, that's the power of composites. And like Cerakote, electroplating helps increase strength, smooths and seals surfaces, and improves cosmetics. However, electroplating also adds another unique property, conductivity. Electroplating applicators can vary the ratio of copper to nickel, so by increasing the copper layer, you boost the part's electrical and thermal conductivity. Conversely, more nickel increases strength, durability, and aesthetics. Now you can see here that the coating thicknesses are greater than what we saw with Cerakoting. So before electroplating, it's a good idea to speak with your vendor before committing to your dimensions. And speaking of vendors, the electroplater of 3D printed parts that comes highly regarded is Repliform. They are based out of the Baltimore area and provide a great service to many 3D printer customers. They also work very frequently with Formlabs parts and give great recommendations. In fact, many of the graphics used in this webinar come from a collaboration presentation between Repliform and Formlabs. Repliform's process involves reception of the lightly post-processed resin part from you, upon which they conduct an inspection. They then etch the part via media blasting to boost adhesion promotion, just like we saw with Cerakoting. Afterwards, the part experiences submersion in a room temperature electroless nickel solution to create a conductive coating for the electroplating steps. Finally, the part undergoes 1 or 2 electroplating steps for copper and nickel each, depending on the part's application. Here you can see the usual process for a cosmetic part. There's a final review after curing, and then the part is shipped back to you. Most of Formlabs resins are capable of being electroplated, but the tough, rigid, and general purpose resins perform especially well. One of the big applications for electroplating is with antennas and gain horns. These often have very complex geometries that are optimized for signal reception and transfer, but are impossible to manufacture using traditional methods. These RF and microwave interacting parts here are actually made by a French company called Elliptica. What was once costing them over $3,000 in 3 months to make is now costing a little over $20 in 2 days to resin print electroplate. Electroplating has applications in other industries too, of course, like jewelry, general manufacturing, prototyping, automotive, and aerospace. And before we wrap up, there are actually even more post-processing options for resin prints beyond the common ones we discussed today. These include additional metal coating technologies, color applications, spray-on rubber coatings, machining, which I know is actually pretty common, and resin prints machine pretty well, but it just didn't deserve a dedicated section. And miscellaneous coatings, things like antimicrobial. I wanted to throw these in here to show you just how many options you have available to you. You know, the buck doesn't stop after printing. But anyways, this is a good time to wrap things up. Thanks for sticking around. I hope this was informative and maybe got your gears turning.